When we look at Earth from space, we see a world defined by its surface oceans. These vast bodies of water cover 71% of the planet, forming the fundamental building block for all known life. However, recent discoveries suggest that this visible water is only a fraction of our planet's total inventory. Deep beneath the crust, locked within the rocks of the mantle, lies a hidden reservoir that dwarfs the seas we know. This water is trapped within the mantle's transition zone, a layer starting 410 kilometers below our feet. Estimates suggest it holds up to 3 times the volume of all surface oceans combined. At these depths, temperatures exceed 1,500 degrees Celsius, and pressures are tens of thousands of times greater than at the surface. Under these conditions, water exists as individual hydrogen ions bonded to oxygen atoms within the mineral's crystal lattice. The sheer scale of this volume challenges our assumptions about where Earth's water resides and how much of it the planet actually contains. For geologists, the transition zone is a realm far more inaccessible than deep space. We can send probes to the edge of the solar system, but we cannot reach the interior of our own planet. The transition zone begins at 410 kilometers. For perspective, the deepest hole ever drilled by humanity, the Kola Super Deep Borehole, barely reached 12 kilometers before the heat made further progress impossible. Physical exploration is prevented by the hostile physics of the deep mantle. The crushing pressure and extreme heat would destroy any mechanical tool or sensor long before it reached the 400-kilometer mark. This created a central mystery in planetary science: how to prove the existence of an ocean so deep that no drill could ever reach it. The answer lies in mineral physics. The upper mantle is dominated by a mineral called olivine. Its crystal structure is dense and tightly packed, leaving almost no capacity to store water. As pressure increases with depth, olivine undergoes a structural change, transforming into a more compact mineral called ringwoodite. Ringwoodite features unique structural voids, acting like a porous geological sponge. It absorbs hydrogen and oxygen atoms, locking them into the crystal lattice as hydroxyl ions. Laboratory experiments in the 1980s demonstrated that these high-pressure minerals could theoretically accommodate up to 2% of their weight in water. Despite the lab success, scientists were at a standstill. Without a physical sample pulled from the natural Earth, the hidden ocean remained a laboratory speculation. In 2014, a discovery in the Joina region of Brazil provided the crucial evidence scientists needed. Artisanal miners working these pits uncovered a small, battered diamond blasted to the surface by an ancient volcanic eruption. Inside that diamond was a microscopic inclusion, a tiny piece of natural ringwoodite. It was a perfect sealed time capsule, preserving a sample of the mantle exactly as it existed hundreds of kilometers below. This was the first piece of terrestrial ringwoodite ever found on the surface. It offered the first chance to test the transition zone's chemistry directly. This table shows the results of the analysis. The ringwoodite sample was heavily hydrated, measuring approximately 1.4% water by weight. This single microscopic inclusion confirmed that the transition zone was not just capable of holding water, but was actually saturated with it. To see if this hydration was a global phenomenon, scientists looked to the entire planet. Seismologists use the speed of earthquake waves to map the interior. Because water-saturated rocks are less rigid, they slow these waves down significantly. Data from the U.S. Array project revealed a massive region of unusually low seismic velocity, exactly at the 660-kilometer boundary beneath North America. This matched the signature of water-saturated rock undergoing a phase change. The convergence of this planetary scale mapping and the microscopic geochemistry of the Joina diamond confirmed the existence of the transition zone ocean. The transition zone reservoir is a moving system, maintained by the deep water cycle over hundreds of millions of years. The process begins at the surface. As tectonic plates collide at subduction zones, the waterlogged oceanic crust is thrust deep into the mantle. When the descending rock reaches the transition zone, it meets the ringwoodite layer. The minerals absorb the water, but because the lower mantle below 660 kilometers cannot hold moisture, the water becomes trapped in a geological bottleneck. As mantle currents push the rock deeper, it transforms again, and the water is forcefully expelled. This triggers dehydration melting, turning solid rock into buoyant magma that carries the water back up toward the surface. This constant cycle of subduction and volcanic release acts as a planetary buffer, helping to explain why surface ocean levels have remained relatively stable for billions of years. These findings challenge the long-held theory that Earth's water arrived late in its formation via comet and asteroid impacts. Instead, the sheer volume of mantle water suggests Earth formed with water already present in its cosmic dust. As the planet cooled, it locked this water inside, gradually releasing it to the surface over eons. This internal water serves a vital function. It lowers the melting point of rock and acts as a lubricant for plate tectonics. Without this hydration, the mantle would be too stiff to convect. Plate tectonics would cease, the carbon cycle would fail, and Earth would eventually become a barren, uninhabitable wasteland. The seas we see on maps represent the visible portion of a massive geological machine. Our surface oceans are effectively the overflow of a planet that holds its greatest reservoir deep within its interior.